So I guess we better start. We're very happy today to have James Millen from King's College London. He's a senior lecturer there, and he's going to talk to us about levitated electromechanics, as you can see. Before becoming a lecturer, when did you become a senior lecturer? Because you started as a lecturer.
I became a senior lecturer about 2 weeks ago.
Congratulations on that. Very well.
Thank you.
So before that, he was a Marie Curie Research Fellow in the Quantum Nanophysics group with Markus Arndt. I do know him, however, from his time in London, when I was in London too. He was actually in the neighboring group with Professor Peter Barker. And while I was trying to show cavity cooling with cesium atoms unsuccessfully, he was pretty successful showing it with massive particles trapped in, I think it was back in the days already, an ion trap. Anyway, at that time, I believe he got used to working with sort of big particles and optomechanics and trapping, those kind of things. But he is originally from a cold atoms background. He did his PhD in Durham University, working with Matt Jones on strontium atoms. But before that, which he had done at Durham University, before that he was at Imperial College London, so you can see that he's always circling around London.
I've played London University bingo. I've got Imperial, UCL and King's now.
Awesome. So thanks a lot for coming, and we are very much looking forward to your talk.
Thank you, Anna, and thank you for the invitation. Just because that was quite a thorough introduction, actually. I find myself increasingly, people approach me because they're considering starting experiments in using nanoparticles, just because there's been quite a lot of success around the world, and a lot of these people, like myself, come from atomic physics backgrounds. And I'd strongly recommend, if any of you ever decide, these levitated nanoparticle experiments are so cool, I'd like to start this, do reach out to people in the community and talk to them, because there's so many little tricks and strange mistakes you make when you imagine that a chunk of glass is just like a big atom with a polarizability that you just never think of doing. And it took us, 5 years to work it out, and it's so boring you can't publish it. This was the difference. In cold atoms, anytime you had a problem, you just look it up in a paper because there's such huge literature. Not true in this field, so do reach out. Great, so I'm going to talk to you today about one particular part of my research activity, which I call levitated electromechanics. And I'll explain what that means as we go through. So here's my research group. Ben Stickler there is in brackets because he's not a member of my research group because I can't afford him, but he's a frequent collaborator of us. For people who missed it already, I'd very much appreciate it if you could navigate to this link in another browser or on a smartphone, because that will allow me to ask you questions throughout this anonymously. It's not a quiz. And already it's been quite useful. So at the start, I saw that the bulk of our attendees are PhD students. So my introduction will be reasonably long, and there'll be a lot of big picture stuff. So I hope everyone doesn't mind that. We're a relatively new research group. Although I've been there a couple of years, our lab was only ready in June 2019. And there's a video of us building the lab. And we're now very full and have built all the way to the ceiling. You can find out more about my research at this link. We keep the website pretty up to date. Okay, so I can skip this one unless people want to practice who've just joined, because you've already voted, and mainly we've got PhD students here. Oh, yeah, even more. And so here's my motivation. My question is, do you believe in quantum physics? And that might seem like a slightly ridiculous question, because of course you believe in quantum physics. But I would take a moment to really analyze your own belief, because someone like Niels Bohr certainly didn't believe in quantum physics, or at least didn't believe in the universal applicability of quantum physics. So he believed that there were objects which could be described by quantum mechanics and objects which could not. If you dig around as to what this actually means, he thinks that a quantum object is something which you can assign a wave function to. And so he would have believed that it would be frankly ridiculous to assign a wave function to a measuring device, for example, almost by definition. Someone like Bohr would have believed that. And so we're going to analyze a little bit why this is a question that's still worth asking and how we might go around answering this question. It's also maybe worth pointing out that Bohr frankly wouldn't have believed that you could do quantum physics even with a molecule, let alone with some of the experiments that have been done nowadays. So, you know, science has moved on. And so people often will go, well, yeah, okay, but we can do quantum physics with all kinds of macroscopic objects. So if you think about the mirrors at LIGO, people have seen correlations between light and the kilogram masses of the mirrors at LIGO. There's these amazing experiments around the world. For example, this one from the Aspelmeyer group, seeing entanglement between, you know, several micron scale mechanical oscillators. And my point here would be that perhaps this is doing quantum physics with macroscopic objects, not doing macroscopic quantum physics, in as much as you don't actually have to assign a wave function to the entire mirror in LIGO, for example, the 40 kilogram mirror, to explain the behavior. And so the question is, can we really do macroscopic quantum physics? And what that would normally mean is to create some kind of unique quantum state. And we'd normally consider a superposition state, because arguably, I would say that's the simplest, not, you know, unambiguously non-classical state. And you want, so if you imagine making a spatial superposition state, then you probably want to make a state with the extent larger than the object itself. So now I'm thinking about something like this very beautiful work, say from Kasovich's group, where you can have a single atom in a spatial superposition state that's large enough for you to walk through the center of. So that is certainly a macroscopically separated quantum state, but with a microscopic object. So now I'm going to quiz you. So you can just click anywhere on this screen. And my question is, what is the largest object ever observed in a macroscopic quantum state? So we like to work in this mass unit, atomic mass units, which I know isn't familiar. So I've drawn some pictures. This is like atomic scale. That's Buckminster fullerene. That's a big molecule. That's a virus. That's a silicon nanoparticle. And that's a bacteria. So put your pointers down. I'm just curious as to where people think the largest object that's been put into a quantum state where the extent of that state is larger than the object itself. I'm seeing some people who definitely know the answer, because I can even see them in their head trying to work out on the log scale the best place to put it. So indeed, if we were to crowdsource the answer, it would be correct. The answer is around here. It's 2.5 times 10 to the 4 atomic mass units. And it's this large, this complicated molecule, which was done by the group of Marcus Arndt and only published last year. So this is a molecule made of about 2,000 atoms. It's a heavily fluorinated molecule. And essentially, they did the double slit experiment of this. But I mean, it's a beautiful experiment. I recommend you either talk to someone from that group or read that paper, because the technology behind that experiment is lovely. I also think there's something that's very interesting here is this is the center of mass interference. So they do interference with the center of mass. You barely need to consider the internal degrees of freedom, the fact it's rotating, the fact it's vibrating. That's kind of independent. And to understand this experiment, you have to assign a wave function to the center of mass of this massive object. Okay. So then my next question is, we did it with a really big molecule. So how about if I got something like a marble, something that's 5 grams? So could I do the double slit experiment with something that big? Would it be just very difficult to do, or would it be impossible by the rules of quantum mechanics to do an experiment with something that massive? I would point out that there isn't really a correct answer to this, except it's not easy. There we go, give you a clue. Yeah, so this is I would say this is a matter of debate, and it's certainly at least difficult. But why might it be impossible? First off, how would we do this experiment? So just a little advert. Myself and Ben Stickler wrote this review article down at the bottom here, which is discussing what kind of quantum mechanics experiments you can do with massive objects. And so to do these kind of macroscopic quantum superposition states, you need first off some source of your large objects. You need to cool them down. That's because if you're in a very broad distribution of states, say for example the energy states of a harmonic potential, then they will tend to average out, and you won't see interference in the end. You won't be able to infer the superposition, and then you do an interference experiment, because it's incredibly hard to measure superpositions directly, because when you do a measurement on them, except in some special cases, you always get the same answer as you predict classically. So you need to do something like an interference experiment to infer that the superposition existed. And so in my field, the work we're doing is we're pushing to create macroscopic superpositions of objects which are at least 10 to the 6 atomic mass units. So that's a couple of orders of magnitude bigger than has been done before. And I mean, people go all the way up to say, trying to do things up to 10 to the 12 atomic mass units even. So this is nanoscale, few nanometer scale particles to microparticles. I hadn't realized I had left this this question in here. So I'm going to go back a slide and I'm going to motivate that one a little bit more. You said it was difficult to produce a superposition state of a marble, but some of you thought it might be impossible. So although I can't tell why some of you might have thought it was impossible, maybe you're thinking about something like decoherence out there. You have to accept what it means if you think it's possible. If you do think it's possible, then what that means is you're accepting the fact that you can put a very massive object at center of mass into a delocalized state, and you can assign a wave function to it. And a wave function is a sum over all of the possible states. And what we know from things like Bell's theorem is that this means that the marble would not have a position assigned to it before you did the measurement, unless you subscribe to some of the less common interpretations of quantum mechanics. So what you're saying is that if you can do this experiment with a marble, then the marble does not have a parameter called its position until you try and measure where it is. And so then my question would be, is the position of the moon defined before measurement? Yeah. And so if you believe in quantum mechanics at all scales, then you have to accept that the position of the moon is not defined before measurement. The role of decoherence is not to collapse the wave function. You should always remember. The role of decoherence is to make superposition experiments very difficult, is to remove coherence, but it doesn't collapse the wave function. So regardless of whether you do an interferometry experiment or not, the position of the moon is still undefined before measurement, if you believe in quantum mechanics at all scales, even if the spread in those possible positions is very, very tiny. And I do think it's worth remembering that, because I think people can be very blasé about the implications of quantum mechanics if you believe it's a universal theory, which, for the record, I do. So what can we learn if we do these experiments? So one of the most important things we can understand is about wave function collapse. Because like I say, decoherence doesn't cause wave function collapse. Measurement causes wave function collapse. So there are various proposals for how wave function collapse might happen in a massive object, such that it is impossible, such that the position of the moon is defined at all times, because maybe it seems a bit ridiculous. So there's these dynamical reduction models, otherwise known as collapse models. And so it's important to realize that these models are not quantum mechanics as we know it. They're an extension to quantum mechanics. So it's a modification of the Schrodinger equation, such that with probabilistic nature, because we know quantum mechanics is probabilistic, objects will become localized in space at a rate which depends upon their mass, which would mean we can still put an atom into a massive superposition, but we couldn't put the moon into a superposition. Nature wouldn't allow it by some fluctuating classical field, for example. And such a fluctuating classical field could, for example, be caused by gravity, which is a different kind of collapse model, not the one I've drawn an equation for there. And so actually Penrose and was involved in this a lot, and Giossi. So there's two ways this could work. You could imagine that you know, everything's moving around, even because of quantum mechanics, the position might be fluctuating, which would cause presumably fluctuations in space-time, because if just the massive objects were moving around, then the gravitational potential would just be fluctuating everywhere all the time. And then if you put a massive object into a spatial superposition, different parts of the superposition will be in different gravitational potentials, and that will give the system enough energy to localize. Or another way of thinking about it is self-gravity. So if I put the moon into a superposition state, you know, what does it do to the gravitational field around it? Does it gravitationally attract itself, for example? Do you get a superposition of space-time? That's what Penrose considered. And somehow these two ideas are completely equivalent in a way I've never understood, but mathematically, nonetheless, you get the same predictions. What's very nice about that is most of these dynamical reduction models at the top here, they have a load of free parameters that aren't physically motivated. And so people just search for them. Whereas the gravitational collapse models make definite predictions about when this would happen. It's just we're not, our experiments aren't good enough yet to see them. Good. Another thing is that if we were to be able to get very massive objects and we were able to do quantum mechanics with them, there are some very practical things that become very useful. These experiments are very hard to do, and the reason they're hard to do is that you suffer a lot from decoherence, coupling to the environment. But if you flip that on its head, it means that these very massive objects are incredibly sensitive to the environment. So there are proposals out there for detecting dark matter using macroscopic objects in quantum states, tabletop gravitational wave detectors, and all kinds of enhanced force sensing, short-range force sensing protocols have been proposed as well. So perhaps it's useful. All right. I'm going to talk a little bit more about how you do these experiments generally. So the first step you have to do is you have to levitate your object. So I'm not going to talk about this much, but if you're interested, at the top is a link to, is a reference to a review article on levitated physics, which kind of covers everything. And so broadly, there are three ways people levitate things. There's optical levitation. So if you have a dielectric object, if you focus an optical field, you get a dipole force on it. That's an optical tweezer. So you can trap pretty much any dielectric in that way. You can also trap metallic particles in this way via exploiting plasmonic resonances, but you get so much heating that there are a couple of experiments which have done this in air, but the heating's so much, if you try and go to any pressure lower than ambient, then your object melts. You can use an ion trap, which I'll talk about more. And then you can levitate anything as long as it's charged. And there's very many different permutations of using magnetic fields to levitate objects. I would say going left to right is increasing the order of complexity of these experiments. Yeah, the magnetic ones are complicated, but very clean and low noise. I'll talk about the electrical one later. The next thing, which I'm not going to talk about in detail, is you have to cool your object down. So normally, I think I'll mention this again later, but normally what we imagine is we get our object and we localize it in space somehow. And that's going to be the source for our interference experiment to infer that we've had a superposition. And so if we want to localize it in space, we need to reduce its position fluctuations. We need to cool it down. We need to make sure it's not occupying a very large space of thermal states, which will get averaged over. So there's loads of different ways of cooling things down. You can use an optical cavity where you can get, there's many different ways of doing that, but you can, so if you're cooling atoms or atomic ions, you exploit the internal resonance of this system to exchange energy and cool the object down. These massive nanoparticles in general don't have an internal degree of freedom, so you don't get this resonant effect, but by using an optical cavity, you can exploit the resonance of the cavity to exchange energy of the optical field. It's sideband cooling. There's also a host of feedback methods you can do. The good thing about working with nanoparticles or larger is they're really big, so they're really easy to detect. So you can just dynamically feed back onto the motion. You can either change the trap depth as the particle moves, which is what this little GIF at the bottom is showing. You just continuously change your trap depth to cool it down, so like Sisyphus cooling. Or you can just apply a force that opposes its motion, well, opposes its velocity, which is called cold damping. And people have cooled particles down to like a few phonons just using feedback methods, which is astounding. This is hundreds of nanometers of size, chunk of material, cooled down to a few phonons. You even see sideband asymmetry just using feedback methods. And more recently, people have used exploited spins embedded within your objects. This is, for example, a chunk of diamond with nitrogen vacancy centers in, and then they can couple to these spins and you can do some cooling this way. So cavity cooling is, in a way, one of the more complex methods, but it's the most successful. And earlier this year, people used a technique called coherent scattering to cool the center of mass motion of a 150 nanometer diameter silica sphere to the ground state of its motion, which is just astounding. So this was done in the Aspelmeyer group in Vienna. So it was an 11-year journey to get this experiment to work. So kind of how it works is you have a particle in an optical tweezer. It scatters light bounces off it, and that light scatters into the optical cavity. So you detune your light so that you only scatter light in such a way that the cavity extracts energy from the motion of the particle. So other cavity cooling techniques involve pumping the optical cavity externally. This pumps the cavity only with light that's scattered from the particle, so it's very efficient. And indeed, they cooled significantly below a single phonon. So on average, this was in the ground state for some amount of time. Yeah, that's very good. So the last thing you need to do is do your interference experiment. As people overlook this a little bit, people are very excited by the ground state cooling experiment, but there's unfortunately 1 million miles between ground state cooling and actually doing interference experiments, mainly because decoherence is a problem. So one thing you can do is a very traditional kind of, double or multiple slit experiment. So you drop your particle through some kind of phase grating or absorption grating, which can be a standing wave of light. And then you let it evolve for some time, and then you can see the interference pattern. So this image at the bottom is the interference pattern when you do this experiment with molecules. And the problem with that is you need so much time for the particle to move through the system, because you have to let the de Broglie wavelength expand, that keeping decoherence to a minimum is almost impossible. A single collision with a single gas molecule is enough to give you which way information in this case. So, I mean, people are proposing doing this experiment in space. That's at a reasonably advanced stage.
Can I ask a question?
Yeah, absolutely, mate.
What is the background pressure that is required
yeah.
for experiments?
Exactly. So in this kind of experiment, so it depends on how long it takes for the particle to go through the interferometer. But in this case, people expect things like 10 to the minus 12 or below millibar. I just pointed out here that the reason that you cool is because if you cool into in a harmonic potential, then the initial slit size gets smaller essentially. So the temperature T as it decreases. So the colder it is, the shorter your interferometer can be. Yeah, but very, very low pressures indeed. Another thing that people forget about is that, of course, to build up an interference pattern, you need to do this experiment many times, and no two nanoparticles are identical, another problem that isn't the same as atomic physics. So this kind of technique, people take very fast. So for example, there's proposals for doing it like in this magnetic skate park, and you can play tricks and you can accelerate the expansion of the wave function. And there's all kinds of ways you can try and do this, but they're really challenging. They require very low pressures. So of course you can do it with atoms. There are many atomic interferometers. So why can't we use that style of interferometer for a macroscopic object? And the main reason is that atomic interferometers rely on coupling to some kind of discrete energy levels, which is at first glance not available for a macroscopic object. So a lot of work which we do in our group is around angular momentum. And angular momentum is super interesting. So first off, because it's discrete from step one. So there's something that's discrete you can exploit. And also because, although it sounds like a tautology, it's non-linear, and there's a lot you can do with these non-linearities. So a lot of the work in my lab, we work with silicon nanoparticles that are actually nanocylinders, and then we can trap or control the alignment degrees of freedom. And so in fact, we can control the rotation so well that we were able to rotate this object at a megahertz, and it only had a microhertz jitter in its line width. So it had a very, very high frequency stability. So you can really control these degrees of freedom very well. And so the idea here is that you trap your nanorod in a laser beam, you cool it down a bit to a few Kelvin maybe, you let it go, it evolves naturally into an angular momentum superposition state. And at some point, these discrete angular momentum states interfere with each other. And the consequence of that is you get a revival. So at some characteristic time after you start the experiment, you will always find a nanorod pointing in the same direction. Whereas classically, that would average out over time if you did it a lot of times. And this is nice because actually it's quite quick. You need less than 100 milliseconds to do this experiment. It doesn't really fall anywhere in that time. So you can just turn your laser beam back on, capture the particle again. And so then you're using the same nanoparticle all the time. And you don't need a diffraction grating in this case. So your whole path becomes shorter, and that's the diffraction grating is also a source of decoherence, of course. So looking for these rotational revivals, which would be, so this is a superposition of the object rotating in all directions at the same time. That indeed would be a macroscopic superposition. The longer you let it rotate, the more macroscopic the superposition becomes. And so that's an experiment which we're actively pursuing. But I'm not planning to talk about that anymore, though I can do. Yeah, I'm not going to talk about the optomechanics more. So another direction is that you can couple the motion of your object, which doesn't have any discrete degrees of freedom, to an external system which has discrete degrees of freedom. And so we have a proposal for coupling a charged particle to a Cooper pair box. So I'll talk about this coupling in the rest of the talk, but very briefly, a charged particle can induce a current in end-cap electrodes, which any ion trappers will know if you've studied the literature back in, like, I don't know, the 70s. And so if you couple that to a Cooper pair box, which is a superposition of charge states, that will map onto a superposition of position states of the particle inside this pull trap. You get very strong coupling. And so essentially what you do is you measure just a qubit, and you do a very fast measurement, and you can infer the existence of a macroscopic superposition in that way. Okay. So now I'm going to talk about like some of the actual experiments in the lab a bit more. And so to motivate why we use ion traps, because a lot of people use optical traps, we're just going to discuss some of the challenges with optical trapping. So one of the challenges of optical trapping is actually the trap depths are very, very low. So maybe there are 10,000 Kelvin or something for nanoparticles, which isn't that many times room temperature, and so they can be very, very unstable. People even have noticed heating due to photon recoil. In general, the coupling you get between optical fields and these nanoparticles isn't that strong. You don't have a resonance here. And so one thing you can try and do is you can try and make all your mode volumes very small. So we did work with some microcavities, but yeah, that's challenging as well. And ultimately, the light you're using just heats the particle up again because you're scattering so many photons from it. So this was very, very nice work where they were cooling nanoparticles continuously and they reduced the gas pressure. That's here. So what that does is it reduces the coupling to the thermal bath. So if you're cooling the particle, it's colder and colder and colder, but this levels out, the number of phonons levels out because eventually you just start scattering you see the discrete nature of the photons you're scattering, and you can't just turn that down because otherwise then you're not levitating your particle anymore. And in fact, if the effective temperature of a laser beam is h bar omega, which is like tens of thousands of Kelvin, it's just in general the coupling to that field is very weak, but not if you're a massive nanoparticle at low pressure. So that's why I wanted to move away from optical fields. And so this is a field which I call levitated electromechanics. And so, as I'm sure many of you know, one advantage for using ion traps is they have these incredibly deep, they're in a very, very deep trap, and you can trap anything that's charged. And so there's lots of people who work with ion traps, myself in the past and Peter Barker's group and many others around the world for looking at nanoparticles. But the difference in the work, which I'm going to talk about, and why I call it electromechanics, being very fancy, is I'm going to have a two-way interaction between my particle and the trapping electrodes themselves. So I've got a very funny ion trap, which hopefully will become clear why I do. So it's a linear pull trap, but it's a linear pull trap with electrodes, which end cap electrodes, which are very, very close to each other, like a millimeter apart. And we can trap single microparticles in there. Just for your information, our particles have charges of around 10,000. Positive charges on the surface, and yeah, they can stably trap for months and months. And the trap depth is greater than 10 to the 8 Kelvin, often a billion Kelvin or more, so they're very stable forever. Good. So here's the motivation. We have our particle that's oscillating some kind of pull trap, and as a charged particle oscillates near an electrical surface, it induces a current in the end cap electrodes. Indeed, this is how people used to detect trapped atomic ions before lasers were invented or became good. But we don't have, such techniques necessarily. And so as the particle oscillates in this pull trap, you can imagine these are the end cap electrodes, and you'll induce a current across this system. And what's very, very interesting, when I started first looking at this project, and I thought it was never going to work, but what's very interesting is that the current you induce is proportional to the charge to root mass ratio. Okay, not the charge to mass ratio. And so what this means is that even though your mass is very, very large, if you highly charge your object, essentially to the pull trap, it starts to look like an atomic ion. In fact, it looks very much, if you very highly charge these particles, they do start to look like a strontium ion or something as far as the charge to root mass ratio is concerned. And also something that's interesting to me is you can trap anything here which is charged. So, metallic particles, organic objects, viruses, for example. Yeah, so that's the kind of idea here. So if you can couple the motion of this object to the end caps, which you hook up into a circuit, if you put a resistance across that, then you can dissipate energy into the resistor. So this is an equation for the momentum of your nanoparticle levitated in the pull trap. And you have this term here that's proportional to the momentum, and that's a frictional term, so that's cooling. And again, this cooling rate is proportional to, or in this case, a charge squared to mass ratio, but that's the same scaling. And so in this way, you can cool the particle just by putting a resistance across. And what temperature do you reach? Well, you just reach the physical temperature of the resistor. So that's very interesting. You know, actually room temperature is quite cold often for these particles when they're first injected. So this technique is still used by people in penning traps to cool down electrons, for example. But you know, you could put your resistor in a fridge and just have 2 wires going to your end cap electrodes, and your object will cool down, which is kind of nice. And you can make the rate much higher by making this a resonance circuit. So that's why I've got REFF, less like an effective resistance. So D is the separation between the end cap electrodes, and eta is one of those geometric factors we all know and hate. But you can go further than this. You can connect the end cap electrodes via some kind of amplifier, and then you can do feedback. So you can take the motion of the particle, induce a current and feed it straight back onto the other end cap electrode. So this is interesting because the current you induce is proportional to the velocity of the particle, not its position. So in this way, for free, you get velocity-dependent forces, which means you get very efficient feedback cooling, which has also been done before for much smaller particles. And then the minimum temperature you can reach in this case is somehow the product between the physical temperature of the resistor, TR, and the noise temperature of the feedback resistor. So you can cool comfortably. You can cool sub-Kelvin even at room temperature. I mean, I did do the numbers. If you really pushed it, if you had a dilution refrigerator and the very best squid amplifier and all of this, then it would be possible using this feedback method to cool an object to the ground state in this way. But I wouldn't recommend it. I'd say that's a really hard route to the ground state. But from earlier in the talk, if you're able to couple to a discrete system, such as angular momentum or a separate discrete system, you don't need to be in the ground state. Just being cold is good enough. Something else we're doing a lot of in the lab is miniaturization. Because everything gets better as you decrease this number D here. So the closer the particle is to the end cap electrodes, actually, like electrode noise isn't such a problem. You find that scales favorably with mass. But yeah, making the system small is good. So that's why I have these funny end cap electrodes, which are very close. It's meant to be picking up the current from the motion in the particle. But we're going a lot smaller actually. So we have these nice chip-based ion traps from NPL, which are massively overkill for us because they're designed for quantum computing, whereas we just want to levitate big chunks of silica in them. But nonetheless, it's very nice having these small ion traps. Especially since you can just like bond some glass to the front of them and you've got a little vacuum chamber. So we're actually just probably next week trying to load particles into that. That's ready to go now. So that's very nice for technology. You can do some nice sensing with that. But I have to say that we haven't actually detected this induced current right now because we got distracted by something else. So let me talk a little bit about the dynamics of the particle in this trap. So this is the Langevin equation for the motion of the particle in one dimension. So you have some term gamma, which is this dissipation rate. So for example, that might be due to collisions with gas molecules. You have your harmonic frequency omega naught, and then you have this white noise term, which is Brownian motion due to a residual gas. So if you look at a time trace of that, you get something that looks like this top trace. I mean, this is data, this is real data from the trap. So you just look in one dimension and you get this kind of behavior. So you see the oscillations and you see the amplitude is varying randomly in time, and that's Brownian motion. So actually, I hope you'll be able to hear this. You should be able to. But I find it very useful. You can convert this data into a sound and hear what it sounds like. So that's what one of these particles sounds like in the pull trap. So you have this frequency, hum, which is this oscillation frequency with some kind of noise level. And so at the bottom left is just the power spectral density, so the Fourier transform of the motion. So you get a very well-defined frequency, which we can fit to theory very well. So that's all just to say it's a very, very, very good model of a underdamped harmonic oscillator driven by noise. So one of the really nice things about using a pull trap and charged particles is that you can exploit the Coulomb force, and the Coulomb force is fantastic because it's so strong. So if you were to add a voltage V0 over here, and this is how it enters into the Langevin equation. So Q is the charge of the particle, mass, and that's that distance from the electrodes. And here I've just included another white noise term. Let's just say it's a fluctuating noise source. But as long as you're at a reasonably low pressure, and that's basically below a millibar, this Coulomb force just completely overwhelms the residual Brownian motion, and you can just ignore the Brownian motion because anything you apply is just so much more significant. And that's very nice because that essentially allows us to do some bath engineering. We can now, using electronics, can engineer our environment for the particle to move in. So we've been looking a lot at binary noise. So actually, I'm not far off finishing now. So binary noise, normally when people think about noise, for example, Brownian motion, they think about white noise. That's some white noise. So indeed, we can put white noise into our system, like truly random noise, and that's kind of fun because you can you essentially just make the particle think is in a much hotter environment. So we can heat the center of mass of the particle up to billions and billions of Kelvin. It's good fun. You can really heat it a lot as long as your trap is deep enough. Yeah. But we're interested in some other kinds of noise. So in particular, I'm interested in this one called telegraph noise, which sounds a little bit different. That's some telegraph noise. That's a very common, something you get in a lot of electronic components. It's often called burst noise or popcorn noise, but it also appears in other bits of nature, and it's random, but it's somehow got a very different spectrum. So we're trying to study the dynamics of particles when they're coupled to these different noise sources. And what's unique about our experiment is whenever anyone else has looked at coupling physical systems to other noise, you always have some white noise bath, which is entirely dominant. It's very hard to avoid that. But for our situation, because the Coulomb force is so strong, we overcome that. So this is just a little plot I put in to show like different timescales. So if you kind of have the transition between two positions. So here we're just putting a voltage on, and we're making the particle skip between minus 500 microns, so a millimeter jump. And if you were to listen to that, you can hear what the dynamics sound like. That's why it's called popcorn noise. Yep, you can hear why it's called popcorn noise now. But we can really play with many different timescales in here. So if I zoom in on that, you can see actually the bath I've coupled to is some other spectrum. And then if you zoom in even more, you can see that it's a harmonic oscillator with a well-defined frequency. So we're having a lot of fun with that. Just trying to see what we can test by coupling to different noise sources. So here's some very preliminary data. So we've been trying to test the fluctuation dissipation theorem when you're coupled to different kinds of noise. So the top left figure is if you so here's a particle, it's just sat in your trap, and you give it a big impulse to somewhere else. So it sits down here, but it takes some time to ring down and settle there. And so in this case, we're doing this while the particle's coupled to a white noise bath, and here we're doing it while the particle's coupled to a bath with a telegraph spectrum. And the fluctuation dissipation theorem can be stated in many ways, but one way is that the response function of the particle chi of t is proportional to the correlation function c of t, and the proportionality constant depends on the temperature. So this is really preliminary data, so I don't want to talk about it that much, but if we do it with white noise, and the different colors are just different runs, then, and this is like many days of data, then you can see you get a really good straight line. And indeed, if you do it with the telegraph noise, you also get a very straight line, but with a different slope, because the telegraph noise has a different effective temperature. So I believe that's the first time that we've kind of proved that the fluctuation dissipation theorem holds for noise that isn't white. The reason we picked telegraph noise, by the way, is you can still do some calculations of it. Okay, that's all I want to say. I'm done, pretty much on time. So like I say, if you want to know more about our research, then we keep our research website up to date very much. And I'm very happy to stay as long as you want and answer questions. That's me done.
Great, James. Thanks a lot for this nice talk, and also for the cool way of participating. I haven't seen that before. That's cool. I'm not sure whether, I mean, you didn't use it much in the later part of your talk, but I certainly, to get an audience engaged, that's very useful. I'm sure there are questions. If you have questions, you can post them in the chat, unmute yourself and ask them yourself. Since I'm already speaking, and I'm very interested in this picture that you have there, this animation, also very beautiful animations, by the way.
Playing with all that research funding.
Yeah, can you go back to that slide where you show this amazing quality factor?
Ah, yeah, of course.
I'm just wondering what it depends on. I mean, what did you show there? What was the signal? I tell you what,
I'm going to show some. Let me just change the slide. So that is somewhat a complex thing you ask, which is fine because I can show you. Yeah, I'll just share my screen again. Okay, you can see it. Just do a nod, I can see. Yeah. Okay, great. So yeah, okay, so rotation is somewhat complex in a way. Hold on. There we go. So if you have a cylindrical shaped particle like this, and you focus a laser beam, then and the light is linearly polarized, then a particle will become trapped in all its degrees of freedom, including the alignment ones, although in this case not the one about its axis. And if you then make that light circularly polarized, you exert a torque via scattering, so you just scatter the photons, and then the particle will rotate. And this is the equation that says how it will rotate. So this is the torque, which you apply on the particle, and it depends on like the laser intensity, the susceptibility and isotropy. So basically like the aspect ratio is the length and the diameter, but you can imagine what it depends on. And then it starts to rotate, and the frequency it rotates at is a balance between the torque you apply by scattering photons and the drag you get by the fact you're moving through a gas. And the frequency spectrum is incredibly broad. So this is data here, a big messy frequency spectrum. And the reason for that is it isn't a resonance. What's happening is the particle sat in the optical trap and it's moving around in the optical field. And as it moves in the optical field, it sees slightly different laser intensities because it's a Gaussian laser beam. That means the torque changes. That means it decelerates and it takes some time to speed up. So it's messy. So instead, what we did is we kicked the particle with circularly polarized light. So nothing fancy, not like a pulsed laser or anything, but we just switch the light from being linear to circular polarization at some frequency, which was just like a square wave, which was a megahertz in this particular experiment. And if you do that, then you go from having this kind of behavior where the particle's freely moving to this kind of behavior. So that's the same scale, the same scale, but now when you kick it. And what happens is the rotor frequency locks to the drive. And it's not as trivial as it sounds. It's actually a kicked chaotic rotor, but it's a very simple chaotic system because there's only two islands of stability that are both very large. One island of stability is this. So you kick the rotor and it just spins in a messy way at actually it'd be half the rate because it's only seen the light half the time, or it frequency locks, and it frequency locks perfectly independent of dissipation to the environment. And I do not have an intuitive way of explaining that to you, but a frequency stability in this case does not depend on any environmental parameter. It only depends on the frequency stability of whatever you're kicking it with. So you basically perfectly transduce the electrical signal from your function generator to this particle and in this rotation. And in fact, the only way you can broaden this is by putting noise on your frequency generator, which is what we had to do. So if you kick this with a signal from an atomic clock, it would rotate without stability.
What's the frequency depend on? I mean, you
showed
it, right?
It's the frequency you switch between linear and circular.
So you can move that frequency wherever you want it.
Almost, because it's still a chaotic system. So there's islands of stability. So yes, to some extent. So you can tune it. I mean, we tuned it by like, a megahertz or something. But if you want to go to like a gigahertz or something, then what you need to be at very low pressure. You need to kick it very hard, and you need quite a high aspect ratio. But you can predict all of that. But then it's still, and so that's how you end up with something like this. But it's not a resonance, so that's not a quality factor. Referees absolutely battered us for that. It's not a quality factor because it's not storing any energy. So if I were to stop kicking it, it would just like spin down. In principle, if I was in really good vacuum, if I stopped kicking it, it would spin like that. But then what is interesting, oh no, this is the chaotic dynamics. This is just very
before you go there, maybe just like you detect it just by scattering, right? The scattering is modulated as a function of orientation.
Yeah, it's like a little lighthouse. And remember, it's like it scatters tons of light, and then you can do a lock-in detection even to really get a fantastic measurement because yeah. So anyway, we proved it was chaotic, but I don't need to go into that. But then what's interesting is that the phase between the kick and the response of the nanoparticle, the phase still depends on some environmental parameters, such as external torque and the external dissipation. So for example, it's a very good probe of any non-conservative force, such as pressure. So it's a really good measurement device for pressure, or say photon scattering. Yeah.
Cool, very interesting, thanks.
Do we have any more questions?
Yeah, exactly. Are there more questions? I, of course, wondered whether you can detect dark matter with it or modulation of fundamental constants.
Yeah, so I mean, the dark matter detection ideas are a little bit, I think they're still a bit controversial. So I mean, it's just based upon the fact that, it'd be really hard if you had a nanosphere that's levitated in vacuum or something, then if dark matter donks into it, you're not going to detect it because the coupling is going to be so weak. But the idea is, instead, if you have a nanosphere in vacuum in a superposition, is the cross-section with dark matter large enough that you will decohere this state because it's so sensitive? So it's like using decoherence as a detection method. And people are thinking about it a fair amount. So as far as I'm aware, and I'm not an expert on this, but the controversy is that somehow some people think the sensitivity is scaled by the fact it's a massive object. They call it like coherent enhancement. So instead of it being like one massive object in a superposition state, it's like 10 to the 9 atoms in a superposition state, so you get like a 10 to the 9 enhancement of the cross section. But I know nothing about this, but wherever my reference was, and it's recorded, so you can go back, Riedel, Jess Riedel is the guy who's done a lot of work on this, but several people are thinking about it now.
I mean, there are two ways, we are trying to detect dark matter with it, and Pavel is here. Maybe one is, for example, with a levitating ferromagnetic needle that Dima Butker mostly is interested in, and like maybe Pavel.
I'm in fact just writing an email about it to James to point out that we think it is possible to constrain dark matter even if it's not in a superposition. I will send you a link.
Yeah, sure. I mean, all of these, actually, it's somewhat interesting. So all of these, like incredibly weak collapse processes that are involved. So the way that people try and infer that they exist, which is a really dodgy way, is that you try and put your particle in a superposition and you fail. And you say the reason you failed is because there's some background which prevents you from putting it in a superposition. And that's a really difficult claim to make, right? Because it could be anything that's making you fail putting your particle in a superposition. But most of the constraints on these collapse models, and I think it's the same in dark matter, right? A lot of the constraints are based on the fact that you should just, if you've got some fluctuating environment, then it will cause an object to move around, will jiggle around, will heat up a bit. And so I think most of the constraints experimentally are put on by people just looking to see if these things are moving around more than you expect. I know people have done this with BECs. So I think, for example, one project Peter Barker's doing is to put a particle in a very, very low noise pull trap. And I see your paper now in the chat. Is to put a particle in a very, very low noise pull trap in very good vacuum and just watch it and see if it heats up. Yeah. Anyway.
Yeah, well, that's what most dark matter experiments are, right? Looking for small effects or nothing. Yesterday we saw a talk, which also, I mean, your talk reminded me of a bit, is detecting like non-standard model forces between objects. And the objects there were one silicon sphere that was basically modulated like spatially. And then they detected this as a magnetic field with a nitrogen vacancy center. Right, so this is one of those additional non-standard model forces experiments where you would need a boson to like be the particle offset force. Pavel also wrote a nice paper about this, and I'm not really in it
so
that much.
I think that's an interesting point as well, right? When people try and say you have these very good sensors with these nanomechanical objects, including the levitated particles. So people like levitated particles. In principle, it's a very good nanomechanical object because you have very low dissipation. But because it's a resonant object, it's only sensitive to forces modulated at its resonant frequency, right? So you have to start playing these games. And so people imagine levitating an object near a surface and then getting the surface and basically doing this or something, right? And then I think to be confident you're detecting a surface force and not the fact that you've got an actuator in there, you have to be really, really confident because they're only sensitive to conservative forces. That's another thing about that rotation, that locked rotation. Actually, it's one of the very few ways I know of very precisely measuring a non-conservative force, a scattering force, which otherwise a nanomechanical oscillator, you're pretty insensitive to scattering forces or DC forces.
Yeah, and how about, I mean, do you trap multiple particles and try to get them to interact? I mean, they probably would interact, right? Because they're charged.
Yeah, sure. You can make beautiful Coulomb crystals if you want to. Yeah, I'm not sure what's useful to do there. I mean, everyone thinks about it and has thought about it. With the optically levitated particles, you can trap a load in a standing wave as well. And I think people have seen some optical binding and stuff, but I think the killer experiment has not yet been found in that field. I was talking to someone actually who yesterday, Christian Schmiglo, is that how you say his surname? And yeah, so he's interested in looking at heat transport in ion chains, right? And I don't know, there might be something interesting in the nano or microscale particles for this, but I don't see why it'd be better than anything else you would do, to be honest. But certainly it's easy to trap lots of particles. One particle's harder.
All right, are there more questions, maybe by someone else?
Yeah, maybe I have one question. How frequent you can load your trap?
Yeah. So we have a particular way of loading our trap, which is, I mean, trap loading is a really technical and dry subject in a way, but coat a surface with our nanoparticles, and then we hit the backside of that surface with a pulse laser, and you get an acoustic shock. Did you have Tracy Northup talk to you at some point, or did I imagine that?
No, we did have actually 2 weeks ago, and we mentioned you and that you collaborate.
Yeah, so that's how she loads her ion traps. And so that was a method which we developed for optical traps in Vienna, and it works for the pull traps as well. It's pretty easy to trap. I mean, I don't know how to put a number on it, but I guess you could load, 10 hertz or something if you really wanted to, which we don't. We want to load 1 and keep it forever as best we can, which you can do with a good. But yeah, for some of these quantum experiments, of course, you would need some, decent repetition rate if you're not able to recapture your particles. But it's lacking for the optical traps a bit. It's a bit more difficult there, both because the trap depth is lower, but also because the trapping volume is very small in the optical traps. It's like 10 microns or something compared to roughly a millimeter in a pull trap. So
thank you.
Any more questions? If that's not the case, I would like to announce the next seminar if I find it on the internet. I announce Quantum Seminar. So next week we have actually a combined colloquium. If you want, we are backpacking of a school that is happening at the MITP, the Mainz Theoretical Physics workshop about the gamma factory. That is something that Dima is very interested in, and we will have Andrei Syrzhikov from the PTB talk to us about atomic physics planned at the gamma factory at CERN. All right, with that, maybe we come to an end. James, that was a really cool talk and a nice discussion. Thanks a lot for joining us.
You're welcome.
And I will just stay here until everybody is gone. But I would say the session is over. Thanks a lot again.
Yeah, thank you very much. By the way, I mean, why I'm asking about the frequency of loading the trap, I may imagine that this could be used, for instance, to fix a sheet on a certain place in the vacuum for further, let's say, preparation also.
What do you mean? So for example, there is a group that they levitate graphene sheets in a pull trap, and then they spin it to get the wrinkles out of it. And the idea is that they can then lay that in places. That's in Maryland. I don't know how we're getting on. I haven't heard anything from them for a few years, but is that the kind of thing you mean?
Yes. Yeah.
Yeah, I don't know. I don't know. I mean, you're probably much better doing that kind of thing in an optical field because you can more precisely position things, I'd have thought.
Cool. And say hi to everybody in London that I at least know and that you meet. So kind regards.
Yeah, I don't know who else I ever.
I definitely managed.
Oh yeah, okay, I will. He's not having a good day today, so I'll let him know. I meet Manish once a week. Manish and I have an hour playing online computer games. It's the only way to keep in contact with him. So.
Yeah, it sounds like it.
Okay.
Awesome. Thanks a lot.
Yeah,
you're welcome.
I will leave now.
Yeah, it's good to see you, Anna.
Pleasure.
Good to see you. Take care.
Okay, bye.